Hi and welcome to another episode of Ordinary Differential Equations. Today we are going to talk about a very famous formula that is typically referred to as Euler's formula. Let's go ahead and take a look at this and see how is that relate to our course. Uh, Euler formula typically written as e to power of I theta is equal to cosine of theta plus I sine of theta. Theta is supposed to be an angle, but in fact it can be any number. It can be even a complex number. Euler was a very famous, very prolific Swiss mathematician who has huge number of contributions to mathematics in other areas. This formula, perhaps second most famous formula in mathematics after Pythagorean formula. You can see it on plenty of t-shirts. In fact, if you type Euler formula t-shirt, you're going to see a huge supply of them. And sometimes a specific angle is chosen to make it the formula to look even more mysterious. Now, what does that have to do with our course? In the previous lectures, we have solved a variety of second-order differential equations. We have given recipe for how to solve them. We can verify our solutions. So for example, if I have this differential equation with the coefficients 10 and 16, my solution turns out to be exponential of minus 2t and exponential of minus 8t. If instead I have 10 and 41, my solution will be exponential of minus 5t times sine and cosine of 40. Make the problem even simpler. If I have y double prime minus 25y, my solutions are exponential of 5 and minus 5. If it is plus 25, it is sine and cosine of 5. Let me make a correction. It's not incorrect, but let me just make it look better. Okay. We can verify that these are solutions of those equations, but there is a nagging thought, like how does the transition from exponential to the trig happen? How is it that we flip from this form to that other form? And is there a way of putting them under the same umbrella? Well, this is the umbrella, and it is the bridge. It is connecting exponentials to sine and cosine, essentially saying exponentials and trig functions belong to the same family. You can go back and forth between the two of them, and that's how the transition from one type to another type is going to happen. Now, in this lecture, I'm going to try to explain the origin of this. Much of the discussion we are going to have is not going to be reflected in the problems that you are going to solve and such, but it's just an attempt to explain the formula itself. You will be using that extensively in circuit analysis, and if you are headed toward mathematics, there is in fact a whole area of mathematics that deals with calculus centered on complex numbers. That is called a complex analysis. So if you wish, you can think of you have had calculus 1, 2, and 3. Well, the story doesn't stop there. There is more calculus to come. So if you wish, you can think about calculus 4 to be complex analysis. It is repeating calculus, but for complex numbers. So what I'm going to do today is I'm going to do a quick review of complex numbers and try to motivate this from what you had in Calculus 2. For the full story, you have to take the complex analysis class. So those of you headed to mathematics definitely will see that. Those of you headed to engineering, that's typically an option that is recommended to many of you, especially if you are going to electrical engineering. Okay, let's go ahead and see what are the complex numbers. So the story, of course, starts with this mysterious number, which due to its mystery was called imaginary unit. I stands for imaginary, so somehow people were just imagining this thing. I squared has a property that it's -1. That's a claim to fame of this particular number. Of course, I is much shorter to write than this symbol, and also helps us avoid a variety of mistakes by writing it that way. So, typical way to write a complex number, we go further beyond the letters X and Y, and toward the end, those Z's and so on are utilized more often when we talk about a complex number. So here's a basic example. 2 plus 3i. This is called the real part of Z, and this is called the imaginary part of Z. So the real part, sometimes they write it like this. The real part of Z is 2. Imaginary part, sometimes they write it like this. I am of Z, and it is 3. I is not repeated here again. Corresponding to this, we have a so-called complex plane. Complex plane looks very much like the Cartesian plane, except that the horizontal axis is reserved for the real component, and the vertical axis is reserved for the imaginary component. So if I have 2 plus 3i, 2 plus 3i refers to 2 steps in the real direction and 3 steps in the imaginary direction, and this is Z is equal to 2 plus 3i. Well, in calculus or pre-calculus, you would have referred to this as just 2 comma 3. But now we are combining the real and imaginary and have this so-called complex number. Now let's go ahead quickly refresh our memory as to how to do arithmetic with complex numbers. Much of it is just very basic standard algebra. The only thing you have to pay attention to is that I squared simplifies to -1. Other than that, there's nothing new here. So suppose I have another complex number t. Then if I want to add them, not a big surprise, the reals gets added and imaginary parts get added. So I have 7 plus 10i. If I want to subtract, nothing new there either. 2 minus 5, so it's -3. 3 minus 7, so -4i. If I have a real number times a complex number like 5z, so this is 5 times 2 plus 3i. Same rules of distribution you have seen before, exact same thing. 10 plus 15i. If I have an imaginary number multiplied by a complex number, suppose I have 7i and I want to multiply by z, so it's 7i. My z was excuse me, let's see, yes, my z is 2 plus 3i. So again, distribution as before, 7i times 2, it's 14i. 7i times 3i, that is 21. I times I is I squared, and that is where the kick comes in. I squared has to be -1, so this becomes -21 plus 14i. That's the only thing that's different from, say, Algebra 1 you had in, say, 7th grade or something. So now if I have t times z, well, what's t times z? T was 5 plus 7i, and z was 2 plus 3i. So this multiplication is exactly like, again, back in almost middle school, that you had the idea of foiling and something, is exactly the same thing. So 5 times 2 is just these, and 5 times 3i. These entries, 10 plus 15i. And then 7i times that, that's going to be, we pick this number here, minus 21 plus 14i. And the result boils down to minus 11 plus 29i. So the multiplication is pretty straightforward, but it's not so familiar to us. Like if I ask you for a factorization of 15, you immediately say 3 times 5. But if I ask you for the factorization of that, it's not so straightforward to figure out that these are the factors. And so there's a whole area of mathematics that looks at that. Now let's move on. We have some new terminology here. One of them is the so-called conjugate. So this is referred to as z conjugate or conjugate of z. So that simply means if I have 2 plus 3i, put a bar on top of it, simply means flip the sign in front of I. So it becomes 2 minus 3i. And in the same fashion, if I had 2 minus 3i and I take a conjugate of that, I flip the sign of this, so it's like a toggle switch, it becomes 2 plus 3i. What is the claim to fame of conjugate? It shows itself in the idea of multiplication. So if I have 2 plus 3i and multiply by its conjugate, which was 2 minus 3i, one of the basic identities of elementary algebra shows up here, which is the following. When you do the FOILing, 2 times 2 is a 4, no problem there. 3i times minus 3i, 3 times minus 3 is minus 9, I squared is minus also, that becomes plus 9. Now 2 times minus 3i is minus 6i, and 3i times 2 is plus 6i. And here is the interesting fact that these two cancel each other out. We get 2 squared plus 3 squared, or just 13. So when you multiply a complex number and its conjugate, out comes a real number. I completely disappears. One of the main uses of that is when you are doing division. Suppose I want to figure out what is t divided by z. What's the ratio of two complex numbers? It's a bit hard to have a direct intuition about that yet, but one way to figure it out as far as the arithmetic concern is to do the following: multiply by the conjugate. That also is the idea that you practice in elementary algebra. When you multiply by the conjugate of denominator, sometimes referred to as a rationalization. It's the same idea. So if I had a t here, what was my t? I forget. T, 5 plus 7i. And the denominator was 2 plus 3i. I want to simplify this. To figure out what that is, I take this and multiply with the conjugate of denominator. What does that do for me? What that does is that it makes the denominator to become an ordinary real number. Simply 2 squared plus 3 squared, that is immediately 13. Now I have to go and actually multiply the numerator. 5 times 2, and that is 10. Let's collect all the reals. 7 times minus 3 is minus 21, but then times I squared becomes plus 21. Then I have 14i, then minus 15i. So that becomes, that is 31 minus I, 13. If you want to insist on what is the real part, what's the imaginary part of that, you can write this 31 13th minus 1 over 13th of I. So this fraction, or this fraction here, this is the real part of it, that's the imaginary part of it. So you probably have seen something like this in pre-calculus. And going forward, you're going to see it in courses like circuit analysis, because there everything is going to be a complex number, and these things are going to represent a variety of actual objects in your circuits. But moving ahead, we are still trying to explain, we are building toward trying to figure out what's the connection between exponential and trig functions. How do we go from one to the other? And we are trying to do this thing in a few minutes. So, okay, our bridge from one to the other is going to go through calculus 2. So we need to go and refresh our memory about some facts from calculus 2. One of the basic ingredients of calculus 2 was series, and particularly the Taylor series. Well, Taylor series are built on top of powers, like you have x and x squared and x cubed and so on. So one thing we need here is, well, we talked about all the basic forms of arithmetic: addition, subtraction, multiplication, and division. How about power? Well, let's go make the problem very simple for ourselves so that we are not spending too much time on this topic today. We are going to start from just the number I and look at the powers of I. So I by itself is just square root of -1, we said. And, well, let's take the powers of that. I squared, this times itself. Claim to fame of that was I squared is just -1. Going up, I3 is, well, you can think about it as I squared times I. So this is minus I. How about I4? Well, you can think about it as I cubed times I, or I squared times I squared. That is perhaps easiest to think about it like that. So -1 times -1, that's going to be +1. Isn't that interesting? There's a number that when you raise it to the power of 4, it becomes 1, but that is, to begin with, it's not 1 itself. Okay, well, perhaps we see the light as to what's going to happen if I go to I5, I6, I7, I8. Let's see if we can pause for a second, and you guys tell me in a second what are each of those powers. Who is I5, I6, I7, I8, and how does it go? What is the pattern? So, well, if we had done I4I, this would be immediate because I4 is 1, and, well, 1 times I is just I. And then we follow the same pattern. So I5 times I. I5 itself is I times another I. It's -1. Faster than that, you can think about it like this. I4, I2. I4 is 1, and I squared is already -1. So that is faster way of getting to the same answer. I7. So let's follow that strategy. I separate how many 4s I have and see what is left. So I4 is nice because it's just 1. And I cube, I have already done it here, so it's minus I. So that's how I do this one as well. This is I4, separate, and then I4. But these are both 1s, so I come back to 1. So we notice that we are going in a cycle. I minus 1 minus I1. Again, I minus 1 minus I1, and so on. So, like if I were I9, I would write it I8 times I1. I'll be back to I again. Here's an exercise for you. What is I to power of, say, 2350, what's your favorite ending number? Say 59. Of course, you don't want to go one by one all the way get there. They will be over. So what's your shortcut for finding that? So let me leave you with that. You think about that. How does how does this help anything with respect to the mystery we are facing? Before I go there, let me give you a little bit of a hint to get this thing for yourself, and a pattern that follows all of these things. For just like the rest of the algebra, we are going to define I0 to be just 1 to make things nice. Then if we look at all of these numbers that we have on the complex plane. So suppose this is my complex plane, and then I to power of 0, that's just 1. I to power of 1, well, that's just I. You come on the imaginary axis, so that is I. I to power of 2 is minus 1, so I came here. I to power of 2 is minus 1. I to power of 3 is minus I. Remember, second component, this is negative, so we are going to go down here. This is I cubed, it's minus I. I4, I'm back here. I5, I'm back here. I6, I'm back here. I7, I'm here. So every time I multiply by I am turning 90 degrees counterclockwise. Every multiplication by I is a rotation of 90 degrees counterclockwise. So that makes sense in the context of this. When we say 2 plus 3i, 2 is like a, think about the vector going straight to the right. 3 would be going to the right also, but if I take a 3 and multiply it by I, it makes it turn 90 degrees, and then it goes up. So 2 plus 3i, 2 to the right, and 3i. So that's one way of thinking about how the complex numbers show themselves on the plane. So what is happening here is in this clock, the same thing. You can use that to figure out what this is going to be. So of course, some students are going to complain, how come you didn't show us how to do this? Well, I gave all the tools that you need so that you go ahead and think about how to do that. It's like I showed you the hammer and I showed you the nail, and then you have to kind of think about how to strike one with the other. So that's what's left for you. Every now and then some problems are going to be left for you to think about and figure that out and be curious about it. Okay, now we are going to go to we said we need to do a quick review of calculus 2. Calculus 2 is a problematic spot for many students because they don't see it in high school, and it becomes a bit of a mystery. But if you have done geometric series in high school, it's not all that bad to go to Taylor series. So here I'm going to do a quick review of Taylor series. So again, before we get lost in the of the algebra, we are trying to explain a bridge between these two, or an umbrella that's going to put all of them under the same canopy. So let's see if you remember exponential of x, cosine of x, and sine of x. These were some of the very basic examples in the Taylor series. Now maybe you need to scratch your head and try to remember what was the Taylor series expansion for these functions, and in fact what was Taylor series. So it's not a bad idea to go do a little search and try to refresh your memory, but before doing internet search, try to see you can recall it from your calculus class. So let's see, what did you come up with? So exponential of x is one of the nicest expansions. It goes like 1 plus, and who's next? X Does that ring a bell? X squared, and what do I have in the denominator? Remember, 2 factorial, and then you have 3 factorial, and so on, so forth it goes. Now, how about cosine? Cosine goes through half of these and flip-flops. It goes to 1 minus x squared over 2 factorial plus x4 over 4 factorial minus, and so on. How about sine? Sine is going to be the odd terms. It's going to be, starts at x, then flip-flops, minus x cubed over 3 factorial and plus x5 over 5 factorial, and so on. Okay, so again, we are trying to squeeze all of this thing in a short lecture. So that's a quick introduction to your Calculus 2 lecture. Okay, now what? Now comes the punchline, if you wish. We are going to apply those to complex entries. To justify that, again, you need the complex analysis class, but we are going to hope that everything's working out. What we are going to do is the following. Here's a plan of the attack. We are going to say, based on this formula, let's go ahead, figure out what is the exponential of I theta. And then check it out against cosine and sine of theta. So that's our plan. A little bit of algebra involved, but not really all that much. So if I write exponential of I theta, how does it go? It starts with 1, and then I theta. I'm going to write it and then square later. Perhaps you want to go ahead of me and clean up this expression. I'm going to write a few more terms of it so that perhaps it helps you to see the pattern that's going to emerge. Write as many as your patience allows. The more you write, the clearer it will be. So you might be wondering, why were we doing this kind of silly looking exercise, powers of I? Well, it's not, no, it doesn't look all that silly because I have powers of I showing up here. So let's go apply that. I have 1. I'm going to take the parentheses off. Take the parentheses off. I have to remember what was I squared. So let me go. I squared was minus 1. So I'm going to clean up a bit. So that is going to be minus theta squared over 2. I cubed, that was minus I. What was I for? Do you remember? And you have 1 second to answer. What was I for? That was just 1. How about I5? So again, think about pausing the video and pushing yourself to come along. I5 was I. Theta 5 over 5. I6, that was, if you remember, you can separate I4, I squared left, I squared is minus 1, so it becomes minus 1. And so on and so forth it goes. Yeah? What do you think I should do? I want to establish a connection. You're building a bridge to sine and cosine. So it's a great time to pause and ask yourself, how do I tie this thing to sine and cosine? I have these rather jungle of expressions. How do I bring some order to this jungle? What should I do here to bring some connection to these and establish some sort of clean order to them? Any ideas what you should do? Of course, if you said collect the real ones and then in another basket collect the imaginary ones, then you're there. So let's go ahead and do that. So I make 2 baskets. My baskets, of course, are parentheses. Here's another basket. That other basket had all the i's in it, so I'm going to factor the I out. So yellows go to basket yellow. I'll have 1 minus theta squared over 2 and theta 4 over 4 factor. And then the other one minus theta 6 over 6 factor. And then all the ones that have i's are going to come to this blue basket. I'm factoring the I out, so there's a theta here. And then here's a minus theta with 3 factorial. Here's the other blue one, so it's a theta 5 over 5 factorial. If I had bothered to write the next one, I7 would have been what? I7 would have been minus I theta 7 over 7 factorial, and so on. So when I factor it, it would have come out here as 7 over 7 factorial. And of course, it does not stop, it keeps going. Do you see the light at the end of the tunnel? You might feel that you are in a tunnel by now, but who is the first? Who is this yellow basket? I hope I haven't lost you. So who is this yellow basket? Pause and look at this screen and see who is it that matches this. Did you find out? Well, of course it is this. Just instead of x I have a theta. This is Taylor series of cosine of theta. And then I, well, by now you know who is this blue basket. The blue basket is this. Instead of x I have theta, so it's I sine of theta. So in brief, we have established what is exponential of I theta. That is cosine of theta plus I sine of theta. So we have established the very famous formula. Let's put it in a nice box. It deserves a degree of respect. So all the other formulas were in some sort of a wiggly box, but this one maybe it deserves a nice table. Okay. So we have established the Euler formula. Then what? Then the question is still, how do we go from one of these things to the other one? How do we go from exponential to trig? Well, if when you're solving this, you come across some complex numbers, you want to interpret exponential of complex numbers, then you have to use that, and then the problem converts to from exponential to trig. So let's, for example, pick this equation that we have. You can do it in general, but let's just pick that one. 10 and 41. These were the numbers that we had. So we are going to go ahead and do the following. So here is the sorry, it's supposed to be a nice line. We want to find the two forms of solutions of this equation and show they are equivalent. Meaning, if we go through that bridge from complex numbers to real numbers, we go from the exponential to the trig, and one type of solution turns into the other one. So we start with the characteristic equation as usual. We go ahead and solve this. So that's minus 10 plus or minus 10 squared minus 4 times 41. So what do I get? R is equal to minus 10 plus or minus 100 minus, that is 164. Inside the radical, we conveniently have a friendly number. So it's minus 10 plus or minus 8i divided by 2. We said we factor before we divide. So r became minus 5 plus or minus 4i. So what do we do then? If we have two roots, we said one style of solution is to write with the exponential of those two roots. So here, this tells me I could have written this as exponential of minus 5 plus 4i t plus b times exponential of same thing but with a minus. Okay, this is a perfectly fine solution. The reason we are going through this whole lecture is to make sense of what does it mean to have a complex exponent. That's the whole fight is all about. So we are going to separate the problem into two pieces. One is the real portion where we have no issue with that, and then the imaginary portion. So I go ahead and rewrite this. This is, I write it as exponential of minus 5t, exponential of 4it, and then again exponential of minus 5t, exponential of 4it. So I distribute it, and exponential of a plus b, you can write it exponential of a plus times exponential of b. Okay, so what we used here is a rule from pre-calculus that if you have one base to sum of two exponents, then it converts to product of two exponential numbers. Okay, exponential of minus 5t, we understand what that is. We don't have an issue with what this one is. So I might as well put it aside so that my clutter is lower. So I have exponential of 4it, and then exponential of here I made a mistake. It was supposed to be minus 4it. Now what? Now we apply Euler's formula. Okay, this real part we leave it alone. Exponential, remember what that was. Euler said this is cosine of 4t plus I sine of 4t. And then Euler again says this is b times cosine of minus 4t plus I sine of minus 4t. This is, we need one more parenthesis here. And to make it clear, these are too many parentheses now. Now I need one little thing from trigonometry, which was negative angle identity, those things that you thought they are of no use. Now here's one place. Cosine of minus theta. Cosine is an even function, and the minus disappears. Sine of minus theta. That is minus sine of theta. So we need that one as well. Now, with that help, I see that exponential of minus 5t is sitting outside. Let me drop some of the parentheses so that the clutter is a little bit less. So if you don't mind, I'll write it a little bit abbreviated. Now, b cosine of minus 4t by this rule is just cosine of 4t. And this one is minus I sine of 4t. Can you think, what am I going to do next? What are we trying to do? We are trying to say that this transitions to that. So what we have here, okay, let's collect my cosines and collect my sines, see what happens. So exponential of minus 5t, a plus b times cosine of 4t. Then what? Then I'm going to put sines in one basket. So sine of 4t, here I have ai, and here I have minus bi. Now a and b were constants. So if you add them, it's some other constants. If you subtract and multiply by an I, that's still another constant. So let's go ahead, call this constant, the whole thing, k maybe, and this one, say L. Our solution becomes what? It becomes exponential of minus 5t times some constant times cosine of 4t, and then some other constant times sine of 4t. So these constants could be any number you want, real, imaginary, whatever. So what we did here is that we started, let's see what happened. We started with a form that we are comfortable with the exponential. We applied the Euler's formula, and after that we have the other form, which is the trig style. So what we managed to show is that Euler formula provides a bridge that takes us from one style to the other style. We had to go through quite a bit of detour for this and go through calculus 2 and pre-calculus and so on to see. So sometimes if you ask a question, we have to be ready for what it takes to take the answer. Like any kid can ask, Dad, why is the sky blue? Or Mom, why is the sky blue? And the parents will say, well, hon, you need to get a degree in physics to figure out why the sky is blue. Yes, the question is very beautiful, and you are very much entitled to the question, but sometimes the answer is a bit more sophisticated, and we have to be ready to pay the price to understand that at a certain level. So that's what it took to figure out why is it that one of these forms translates to the other form. Okay, I hope you came along. Let me just write down a couple of additional exercises so that we have something here that everybody can easily appreciate. So, for example, what is exponential of pi third I? Well, okay, I hope you're not tired by now. Euler formula tells us what? Just take a couple of seconds to tell me. Euler formula says this is cosine of pi third plus I sine of pi third. Well, we have picked a friendly angle. So another issue from trigonometry. Do you remember what was cosine of? Same as 60 degrees. Cosine of 60 degrees was what? Do you remember? Of course, 1/2 plus I. Sine of 60 degrees was radical 3 or 2. So sometimes you are asked what's e to the power of I pi. So that's cosine of pi plus I sine of pi. Well, cosine of pi, who's that? -1. Sine of pi is 0. So this thing boils down to -1. So we see that exponential of I pi is -1. Sometimes this is brought to the left-hand side and it is written like that. And this is one of the formulas that you see on t-shirts sold by math department or engineering department. The mystery of it is that all the famous numbers of mathematics are here. 1 and 0, well, we know all about them. E and pi come up next, and I is the fifth element of this group. All of them are under one umbrella. Okay, I hope you enjoyed the lecture. In the next lecture, we are going to look at more applications of second order equations. Until then, I leave you in this picture. So good luck and God bless.